All right, we're back. We are still on page 3 of note 17 of Calc AB. We're talking about the second fundamental theorem, which really means we're talking about accumulation functions and their rates of change. An accumulation function is just a function that has a definite integral in it. They're a big deal. They come up all the time, in particular because it allows whoever's asking you questions to give you a graph and ask you questions about that graph on like several different levels at the same time. So they're really common. So here's the problem that we're given. The function g of x is defined by g of x equals the integral from -1 to 2x of f of t dt, where f of t is between -4 and 4 and is shown below. So this graph that we are looking at is the graph of f of t, which means this is the t-axis. All right, so that's all stuff that we need to know. Now the first question is, what is the domain of g of x? All right, so that's weird. G of x. So what I'm going to do, I'm going to rewrite g of x over here. So g of x is going to be the integral from. Now I'm going to make it really explicit what these variables are, what the bounds are rather, right? So it's dt, which means these are t values. T equals -1, t equals 2x, and then f of t dt. And it is because that this is dt, that these are t values. That's something that, when you take Calc AB, Calc BC, not super, super important because you don't get messed up a lot. When you take Calc 3, keeping track of what the bounds are relative to the differential, the dt, can be huge. So if you start focusing on that and noticing that, life will be easier for you. Now, why is this important? Well, look at our graph of f of t. For our graph of f of t, we know that t can be anywhere between -4 and 4. So my explanation, let's start building it. So from the graph of f of t, actually it's just given. I don't even need to say from the graph, right? It's actually given in the original. So let me delete that and just say it's given that t is between -4 and 4. So I should also use a marker instead of the lasso tool. It's given that -4 less than or equal to t less than or equal to 4. Okay, so once we know that, the upper bound of our integral is t equals 2x. So from the integral, so from g of x, basically, we know that t is equal to 2x, right? That's the upper bound. So what does that mean? Therefore, if -4 is less than or equal to t is less than or equal to 4, and t is equal to 2x, we know that -4 is less than or equal to 2x is less than or equal to 4, which means -2 is less than or equal to x is less than or equal to 2. That's the domain. Our domain is going to be -2 to 2. So if you look at our function, we can kind of like play around with it a little bit, right? So say you want to find g of 0. G of 0 is going to be the integral from -1 to 2 times 0, so -1 to 0. It works, no problem. What is the biggest value you can think of that you could sub in for x so that you can still find the definite integral using this graph? Well, in my mind, the biggest thing I could sub in for x up here would be 2, because if I sub in 2, I'm going to get the integral from -1 to 4, and I know I can't go higher than 4, so that upper bound of the domain of 2 seems to make sense. The same argument works for the -2, and so that's why I think that that's the domain. I mean, I know it's the domain, but I think once you get the domain, like stop a second and think like, does the domain make sense? Because if it definitely doesn't make sense, then it might be wrong, and you actually need to revisit that. So the next question is to create a graph of g prime of x. All right, well, to do that, I'm going to need to know what g prime of x is. So g prime of x, this is a second fundamental theorem problem, right? So we take the integrand, which is f of t, replace every t with 2x. So it's going to be f of 2x times the derivative of 2x, which is 2. So g prime of x is just going to be 2f of 2x. Okay, so I'm going to copy that down here so that we know that. So g prime of x equals 2f of 2x. All right, so now there's a lot of ways to create this graph. Basically, think of your transformations. What we're going to do is we're going to take every y value on the graph of f and double it. So the original graph is between -2 and 2. The graph of 2 times that will be from -4 to 4. So that's going to be a part of our answer. So I'm going to actually start a set of axes here so that I can get going on that. Okay, so this I'm going to say is like -4, -2 here, here, and maybe like 4, 2, and here, let's say. Okay, now the domain we know for g of x is -2 to 2. So the biggest domain that g prime could have would be -2 to 2 because the domain cannot get bigger when you take a derivative. So what I'm going to do is I'm going to say this is -2, -1, 1, 2. And we could put in the little extra half tick marks just in case. Just in case, maybe this is the second time I've made this video, and the last time it stopped working halfway through. Who knows? Maybe I know that those halves are important. All right. So what's the easiest thing to do here? I think the easiest thing to do is to look at the key points that are on the graph of f, and we'll transform those so that they will be on the graph of g prime. So I don't actually know if that one's important. I mean, it's important, but it's not like a key point because like we just want to connect lines or dots. So what I'm going to do is I'm going to say to myself, what values, so can I make a chart? So what are these key t values? So I'm going to say, oh boy, t, and then x, and then g prime of x. Okay, so why is that the order that I'm going in? Well, I know the t values because this graph up here is f of t. So I know the t values of the key points. So the t values are going to be at 4, at 2, at 1, at -1, possibly -2. I'm going to skip that one, -3, and -4. Okay, what's the relationship between t and x? Well, t is equal to 2x from the upper bound of our thing, which means if t equals 2x, then x is t over 2, right? So at 4, we're going to end up with our x coordinate is 2, 1, 1/2, -1/2. Why is this so small? -3/2, -2. Okay, so now g prime of x, which we know is 2f of 2x. Okay, we're getting there, right? So g prime of 2 is going to be 2f of 4. F of 4 up here is 1. 2 times that is 2. Okay, g prime of 1 is going to be 2f of 2. F of 2 is 2, so we'll double that to get 4. At 1/2, we double it, we get 1. 2f of 1 is -2. 2f of -1 is -1 gives us -2, so we double that to get -4. 2f of -3, f of -3 is 2, so double that to get 4, and then the same thing here. All right, so I'm going to plot these points, x comma g prime of x. So 2, 2, and then 1, 4, and then we're going to put a line segment between those. And then 1/2 -2, so 1/2 -2, so there. And then -1/2 -4, it's going to be like down here. And then -3/2, 4 is going to be up here, I guess. We just connect this. And it does make sense that this -2 that was here corresponds to that -1. That makes sense, right? Because you cut the t value in half to figure out the x value. So that's working for us. And then here, So this is, I mean, this is like labor intensive. It's probably more work than when I originally wrote the problem I really intended it to be, but I think it's good. I mean, you get to think about transformations, you get to think about a lot of things. So the next question, what are our next questions? Relative minimum, and then increasing concave up. Relative minimum, that's so unfortunate. All right, so I'm gonna need to know, I think. So relative minimum is when the derivative changes from negative to positive. So when G prime goes negative to positive, if you look at G prime, the place where that happens is right there. So increasing concave up is going to be when I don't know what question I'm answering. Question C is, when is G of X increasing concave up? So we're increasing concave up whenever the derivative G prime is positive, that'll be increasing. And then concave up means that the derivative is increasing. So we need the derivative to be increasing and concave. Wait, no, we don't. Oh my God. This is, you know, after the last video didn't work, I should have just stopped for the day. But I was like, no, I'm going to finish this page. And so here I am. All right, so G of X is increasing concave up when G prime of X is positive and increasing. Okay, so now I need to figure out when that is happening. So when is that happening? Well, that's actually only happening on this interval right here. So I need to figure out that x coordinate. So is that a convenient x coordinate anywhere? Not really. So I think I'll just do it here. All right, so this point is 1, 4. Maybe I'll use a different color to like show that I'm doing some extra weird work here. This point is 1, 4. This point right here is negative 1/2, negative 2, negative 1. Oh, positive 1/2, negative 2. 1/2, negative 2. Okay, so the slope of that line, so let's do this. The slope of that line is 4 minus negative 2 over 1 minus negative 1/2. So this is a great slope. 6, and then you know what I could have done is I could have, well, it's all right. I could have used this, right? And we're just doubling the slope. So like, what is this? It's up 3 over 1, so 3. So I think the slope when I double it should just be 6. But let's see if we get that. It's not looking like I'm going to get that, so I'm not sure what's wrong with my intuition there. Maybe I was not double it. I mean, it should be twice as steep because I doubled it. What is this? 3 over 2. So I'm getting 12 over 4. I'm getting 3. Does that make sense? That doesn't make any sense to me. So what did I do wrong? 1 minus positive 1/2. Come on, man. There we go. That's 1/2. All right, so this is 1/2. So I get 12, which is double what I was expecting. Why is that? Why is that double what, I mean, it looks, 12 feels right. I mean, I go up 6 and over 1/2. So like, yeah, that's definitely 12. Is there a reason I was supposed to get that? And like why my intuition is failing me here? Don't really know. Doubled it. Don't really, it's like I doubled it twice. I want to think about that. Maybe I'll come back to that in another video. But I'm pretty confident that slope is supposed to be 12. So then the equation of the line would be y minus 4 is 12, x minus 1, or x minus 1. So then if I set that equal to 0, I'll get negative 4 is 12, quantity x minus 1. Negative 1/3 is x minus 1. So x is 2/3. That feels like it makes sense to me. So I'm going to say that therefore on So I'll use an inequality. So 2/3 to x to 1. So I think that that is the interval on which g of x is increasing and concave up, right? Because we need g of x to be, we need g prime to be positive, and we need g prime to be increasing. I think that happens from 2/3 to 1. So yeah, I think that's a good answer. Relative minimum. Fortunately, the only location of a relative minimum is where the derivative goes negative to positive. The only place that's happening is also at that value we just found. So I'm going to say g of x has a relative minimum at x equals 2/3 because g prime of x changes negative to positive there. And that's my justification. So all I need to do is I need to say the x-coordinate, and I need to say that the derivative changes from negative to positive, because that's what's going to give you a relative minimum. So I think what I'm going to do is end this video here. There is that weirdness about the 12, and I'd love to work out why intuitively that doesn't make sense to me. There is like, so I think, okay, I think that I know what it is, right? So I think, right, basically the slope of the original is 3, right? Because you go over 1 and you go up 3. So that's 3. So what we do is we cut the x values in half, which actually, without changing the y values, would make this thing steeper on that interval, right? Because you still have to go from -1 to 2. You still have to go up 3, but now you're only doing it in 1/2 the time. So your slope for f of 2x would have been double. It would have been 6. But then, because the chain rule gave us another 2, we doubled it again. So this is kind of neat, because I don't think I've ever thought about that before, like what happens with the slopes as you like compress. But it makes sense that it gets steeper, so that made it steeper by a factor of 2. The chain rule gave us another 2, so we went from 3 to 6 to 12. I'm okay with that. I think we got that. All right, so I'm going to end this video here. I will come back in the next video and do some more, probably on a different day though, because man, I've had a long day. So I hope to see you there.